Now, a common example on base excitation, as in problem 251, talks about a vehicle driving over a rough road. The vehicle can be simply modeled as a single degree of freedom, as a simple quarter car model, as a mass and spring and a damper, both connected to a wheel that is driving over a rough road. Now, given the parameters, the stiffness of the spring and the damper constant and the mass, and here's the excitation term, y is 0.01 meters, and this is the excitation frequency, the base frequency, and we need to determine the amplitude of the vehicle motion. We need to find the maximum amplitude x of the motion. This is straightforward actually problem, because we know that x is equal to y times 1 plus 2 zeta r squared divided by 1 minus r squared all squared plus 2 zeta r squared all under square root. So all I need to do is to find r zeta and y is given, so that I can determine x. So first of all, r is omega base divided by omega natural frequency. So I need to find omega n, and omega n is the square root of k over m, which is, in our case, square root of 3.273 times 10 to the power 4 divided by the mass of the car, which is 1007, and that would lead to a natural frequency radians, of course, per second. Now notice that this frequency looks close to the excitation frequency, so I expect a large amplitude for x. Now r, I'm dividing omega b, which is 5.818, divided by 5.701 to get the frequency ratio. It will turn out to be 1.021 approximately. Zeta is, I know that C over M is 2 zeta omega n. So I can substitute the values for C, M, and omega n. C is 231, M is 1007 equals 2 zeta, and omega n is 5.701. This leads to zeta equals 0.0201. Now, given this zeta and r, I can substitute both zeta and r, and I know that y is 0.01. So I can plug all these numbers into this equation, and solving for x, x will turn out to be 0.1716, which is way much larger than the excitation amplitude. Y is 0.01, but the response is approximately 17 times the excitation amplitude, 0.01 to 0.17. That's 17 times the amplitude. And why is that? Because R is almost 1 and the damping ratio is very small. So if you recall the R and transmissibility plot, it was near R equals 1, goes to very large value, especially when zeta is very small. This zeta is near 0, so we're talking about something that's very close to zeta 0, and here you will have huge amplification of the excitation. The distance transmissibility is 17 approximately. If you divide x by y, x divided by y, which is the distance transmissibility, you will get 17.16, 17 times the excitation amplitude, and that's because of resonance. Now in problem 252, we have a mass on a moving support, and it's given that the mass is 250 kilograms. The stiffness of the spring is 32,000 newtons per meter, and the mass is observed to move with a maximum amplitude of 10 millimeters when the amplitude of the base motion is only 2.5 millimeters. Based on this information, we need to find the damping constant. C is unknown, so we need to find C. Now, going back to this expression right here for distance transmissibility or displacement transmissibility, x over y equals to 1 plus 2 zeta r squared 1 minus r squared whole squared plus 2 zeta r whole squared under square root. Okay, I know what x is, I know what y is, and I need to find c. C, basically, if I want to find c, I know that c over m is 2 zeta omega n. So if I'm to find zeta and omega n, then I can find c. Now first, omega n, this is easy to find, which is omega n is the square root of k over m. K is given and m is given, and omega n will be 11.31 radians per second. Now the other piece of information given is that this happens at resonance. The problem says that this motion is observed at resonance, which means that if this is at resonance, means R is equal to 1. That's why if you notice the transmissibility here is 10 divided by 2.5, that's 4, greater than 1 transmissibility. So substituting R equals 1 and X and Y, X is 10 divided by 2.5 is equal to 1 plus 2 zeta squared divided by R is 1, so this is 0, and 2 zeta squared, all under square root. Here I can solve for zeta, and zeta will be 0.1291. Now I have zeta, I have omega n, I have m, which is 250 kilograms, so I can substitute in here and solve for C, and C will turn out to be 730.3, and the units are kilogram per second or meter per second. Newton second per meter.